far we have studied 3 coding strategies. These are Shannon coding, Fano coding and Huffman coding. We have proved that Huffman code is optimal in the sense that the expected or average code length for the Huffman code is minimum. Now, let us discuss a bit more about the code word lengths for Huffman codes and Shannon code for some specific source alphabet. Huffman codes and Shannon code, we look at these 2 codes and look at the word lengths. Now, using code word lengths of log 1 by pi, which is called Shannon coding, this may be sometime much worse than the optimal code for some particular symbol. Let us take an example that I have a source, a binary source consisting of 2 symbols S1 and S2 with the probabilities given as probability of S1 is equal to 0.9999 and probability of S2 given as 0.0001. Now, if we use the Shannon coding strategy, then we can calculate the number of bits which we should allot to the source symbol S1 as log of upper flow of log of 1 by P1, and that will come out to be 1 bit. And for this, the upper flow of log of 1 by P2 will be equal to 14 bits. Optimal code word length is obviously 1 bit for both the symbols S1 and S2. Hence, the code for the infrequent symbol is much longer in the Shannon code than in the optimal code like Huffman code. Now, is it true that code word lengths for an optimal code are always less than upper flow of log 1 by pi? Let us answer this question with an example of an illustration. Let us assume that I have a source consisting of 4 symbols with the probabilities given as 1/3 probability of S2 equal to 1/3 probability of S3 equal to 1/4 and probability of S4 equal to 1 by 12. Now, for this source we can design an Huffman code, and the code word lengths which will result from the design of the Huffman code will be 2, 2, 2, 2 or 1, 2, 3, 3 depending on where one puts the merge probabilities in the process of Huffman coding. To get this, we follow exactly the same procedure which we had discussed in the last class. Now, both these Huffman codes achieve the same expected code word length. In the second code, that is this, the third symbol has length 3, which is greater than log of 1 by P3. Thus, the code word length for a Shannon code, which will be decided by this, could be less than the code word length of the corresponding symbol of an optimal Huffman code. Huffman code is optimal in that it has a minimum expected length, but what does that say about its performance on any particular sequence? For example, is it always better than any other code for all sequences? Obviously not, since there are codes which assign short code words to infrequent source symbols. Now such codes will be better than the Huffman code on those source symbols. It would be interesting to relate the code word lengths, at least in probabilistic sense, of say Huffman code or Shannon code to the code word lengths of some other uniquely decodable code. Now for notational convenience, and this in turn will result in the simplification of our understanding of the concepts to follow, we will follow the following framework. We will denote the output of a source as a random variable. So the output of a source will be denoted by a random variable x with the source alphabet given by this, and we will denote the probability mass function Px, that is equal to probability of the random variable x equal to x, where x belongs to the alphabet. And we will also denote this probability mass function Px by, we are denoting this by rather than by this notation just for convenience. So if you want to denote a really speaking probability mass function for random variable x, we should denote it by this term, but just for the sake of convenience we will denote it by a simplified form as just Px. Now dealing with Huffman codes is difficult since there is no explicit expression for the code word lengths. Instead we will consider the Shannon code, because for the Shannon code, code word lengths like Lx can be specified as equal to log of 1 by Px. Such explicit expression for the code word length of Huffman code is not possible, so it will be difficult for us to consider Huffman code. So we will consider the Shannon code, and for the Shannon code we have a following important theorem. Let Lx be the code word lengths associated with the Shannon code. And let L dash x be the code word lengths associated with any other code, then the theorem says that probability of L x is greater than equal to plus a constant c is less than or equal to 1 by 2 c minus 1. What it means that the probability that L dash x is say 5 or more bits shorter than L x is less than 1 by 16. So, the interpretation of this is given as explained. Now, let us look into the proof of this. So, probability of random variable greater than L dash x plus c is nothing but probability of log of 1 by p greater than or equal to this implies this, because the length is given by the upper flow of 1 by p x for the Shannon code. Now, this quantity is less than or equal to probability of log of 1 by p of x greater than or equal to length dash L dash x plus c minus 1. I can write this expression because log of is less than or equal to log of 1 by p x plus 1. Because of this, I can write this expression. Now, this interpretation in terms of probability is nothing but probability of x less than or equal to 2 minus L dash x minus c plus 1. Now, probability of this random variable is nothing but a summation of the individual probabilities, where I have to sum up for all x which satisfies p of x less than or equal to 2 minus c plus 1. So, this is equivalent to summing up the probabilities of x, where x is all those x for which probability of x is less than or equal to this quantity. Now, I am summing this up for all p x less than this quantity. So, what it implies that this quantity itself is less than or equal to summation 2 minus L dash x minus c plus 1 for this is the upper bounds of p x. So, that is why it becomes less than or equal to. Now, this is obviously less than where I sum up for all x. So, 2 minus L dash x minus c minus 1. So, this is equal to now this quantity is the Kraft's inequality. So, summation of 2 minus L dash x x, if I assume that the code which I am considering is uniquely decodable, then this should satisfy Macmillan's Kraft inequality. So, this is less than equal to 1. So, what it implies that this quantity is less than equal to 2 minus c minus 1. So, now we have proved that no other code can do much better than the Shannon code most of the time. So, it is a very important result. Now, pertaining to a Shannon's code, there is another important theorem which we will have a look at it. So, suppose I have the code word length Lx for the Shannon code and L dash x as the code word length for any other uniquely decodable code, then what one would like to ensure is that Lx is less than L dash x more often than Lx is greater than L dash x. So, this is something which is desirable, that I want Lx which pertains to the Shannon code is less than L dash x which pertains to any other uniquely decodable code. This should happen more often than this. So, that means probability of this should be more than this. So, let us try to prove that, but before we try to prove that, let me define what is a dyadic probability mass function p x. Now, probability mass function p x is dyadic if log of 1 by p x is an integer for all x. X comes from, is a discrete, and it comes from the alphabet this x. So, if log of 1 by p x is an integer for all x, then probability mass function which is given by p x is known as dyadic. Now, with this definition, let me study another important theorem. The theorem says that for a dyadic probability mass function Px, let Lx equal to log 1 by Px be the code word length of the binary Shannon code for the source and let L dash x be the length it is code word length of any other uniquely decodable binary code for the same source. Then the theorem says that probability of Lx being less than L dash x is greater than probability of Lx being greater than L dash x, and this is with equality if and only if L dash x is equal to Lx for all x. Now, we can say thus the code word length assignment of the form Lx is equal to log of 1 by Px, that is the Shannon's strategy, is uniquely competitively optimal. So, we have proved that Huffman code is optimal in the sense that the average or expected code length is minimal. But now what we are going to prove is that Shannon code is uniquely competitively optimal, and by that we mean that probability of Lx being less than L dash x, the probability of code word length for Shannon code being less than code word length for any other uniquely decodable code is always greater than probability of code word length of Shannon code being greater than the code word length of any other uniquely decodable code. A very important result, though this result we are trying to prove it for the dyadic probability mass function, then we will try to relax this condition and see what happens. Okay. So, the proof follows as follows. Now, before we have a look at the proof, let me define one function, that is the signum function, and define the function signum t as follows. Signum t is defined as it is equal to 1 if t is greater than 0, is equal to 0 if t is equal to 0, and it is equal to minus 1 if t is less than 0. Then based on this definition, it is easy to see from the following figure that signum t will be always less than or equal to 2 raised to t minus 1 for t equal to 0 plus minus 1 plus minus 2. So, if we draw the plots for these two functions, they will appear something like this. This is your t and I plot my function. So, this is my signum t, and this function is 2 raised to t minus 1. So, from this is a plot for 2 raised to t minus 1, and this is a plot for the function signum t. From this plot, it is very clear that signum t is always less than or equal to 2 raised to t minus 1, but it is very important to note that this is valid only for t equal to 0 plus minus 1 plus minus 2. So, it is for all the integer values this is true. And 2 t minus 1, when the t tends to negative, it is bounded by minus 1. So, this is result is always valid. Okay. Now, based on this result, we will try to prove the theorem. So, this is not valid for all t, but is valid only for integer values of t. So, based on this, we can now write probability of L dash x being less than L x minus probability of L dash x being greater than L x. This I can write, this probability I can write as probability of x, where I consider only those x for which L dash x is less than L x, the probability of the random variable. So, by definition it is this, and this is nothing but the probability of the symbols for which L dash x is greater than L x. Now, this itself it is not very difficult, that this I can write as summation of p x, this is signum of Lx minus L dash x over all x, simple from here to here. Now, this by definition is nothing but expectation of signum function Lx minus L dash x. This follows from the definition of expectations. Now, because we have seen that signum of t is always less than or equal to 2 raised to t minus 1 for t equal to 0 plus minus 1 plus minus 2, and since our difference between these two random variables are always integers, we can use this relationship to write as summation of x px 2 of raised to Lx minus L dash x minus 1. So, let me just denote this relationship out here by A. We will come back to this little later on. So, I denote the step out here by A. Now, based on this we have come from here to here. Now, this I can simplify because my Px, because it is a dyadic probability mass function. So, Px is nothing but 2 raised to minus Lx. So, I can write this as summation of x 2 raised to minus Lx minus 1, and this you can simplify as x 2 raised to minus L dash x minus 2 raised to minus Lx x. Now, this quantity is nothing but the Macmillan's Kraft inequality. So, if your L dash x is a corresponds to the code word length of another uniquely decodable code, then it implies that this quantity has to be less than or equal to 1. So, I can say that this is equal to less than or equal to 1, and this is obviously 1 because it is a dyadic probability mass function. So, summation again is equal to 1. So, let me call this relationship as B. So, this quantity out here is going to be less than or equal to 1. So, I can write this as less than or equal to 1 minus 1, and this is equal to 0. So, what we have shown now that this is less than or equal to 0, where this step A follows from this, and B here we have used the Macmillan's Kraft inequality. Now, we have an equality in the above chain here at A and B. So, if we have equality in the bound for signum which occurs only for t equal to 0 or 1 in this case, then if we want to have equality out here, then what it means that Lx is equal to L dash x or Lx is equal to L dash x plus 1. This is I can write because the signum function, if we look at the signum function, the equality holds for t equal to 0 and for t equal to 1. So, in our case here, if I assume that the equality is at this point, then t equal to 0 and t equal to 1 corresponds to Lx is equal to L dash x and or Lx is equal to L dash x plus 1. Another equality is, if you want the equality, then this at point B, this should be equal to 1, which implies that the Kraft inequality is satisfied, and combining these two facts we will get L dash x is equal to Lx for all x. So, this we get from equality A. I mean, when we assume the equality A, when we assume this condition that t is equal to 0 or 1 at this point, and here we assume that this also satisfies the equality of Mackman-Kraft equality, and then from both this condition we will get L dash x is equal to Lx for all x. So, we have proved the theorem. So, we have proved that this probability is always greater than this for the Shannon code. So, after having proved that the Shannon code is uniquely computatively optimal for a dyadic probability mass function, for non-dyadic probability mass function there is a corollary, and I will just state the corollary for the sake of completion without the proof, but the proof is follows along the same line as the proof which we saw for the dyadic probability mass function. So, the corollary for the non-dyadic probability mass function would be, for non-dyadic probability mass function, expectation of signum Lx minus L dash x minus 1 is less than or equal to 0, where Lx is upper flow of log of 1 by Px, and L dash x corresponds to the code word length for the source, but this is another uniquely decodable code. So, L dash x is any other code word length. This is a uniquely decodable code for the source. So, an important result, what it says that on the average the Shannon code will provide the code word lengths which does not differ from the code word lengths of any other uniquely decodable code by 1. So, important relationship. Okay. After having studied this, now let us go back to the Huffman code. Now, we had looked into the procedure for the design of a Huffman code where our code alphabet was a binary in nature. So, now let us look at the procedure to extend the binary Huffman coding to a non-binary Huffman coding strategy. So, in the non-binary Huffman coding, what we mean is that the code alphabet is size is not 2, but greater than 2. So, the binary Huffman coding procedure can be easily extended to the non-binary case where the code elements form an array alphabet. So, let us study non-binary Huffman codes. Recall that we had obtained the Huffman algorithm based on the two observations, that first, that the symbols that occur more frequently or have a higher probability of occurrence will have a shorter code words than symbols that occur less frequently. And the second observation was that the two symbols that occur least frequently will have the same length. And we added an additional requirement that the two symbols with the lowest probability differ only in the last portion. Now, we can obtain a non-binary Huffman code in almost exactly the same way. The obvious thing to do would be to modify the second observation, which would mean now that the R symbols, R denotes the size of the code alphabet. So, the R symbols that occur least frequently will have the same length. That is the modification of the second observation, and we will also modify the additional requirement to read as the R symbols with the lowest probability will differ only in the last position. However, we run into a small problem with this approach. Consider design of a ternary Huffman code for a source with 6-letter alphabet. Now, if we use the rules described now, then in this case what we would do is we would first combine the 3 letters with the lowest probability into a composite letter. So, that we would be doing at the first stage. So, after the first reduction, we will get from 6 letters alphabet, we will move over to 4-letter alphabet. Now, once we move over to the 4-letter alphabet, and if we follow the same procedure of combining 3 letters into a composite letter, then at the end of the second stage of reduction, I would be getting 2 letters. So, finally, I have a 2 letters reduced alphabet, and I have 3 symbols to be allotted. So, this is the one strategy which I could have followed. Another strategy which I could have followed was that to start initially I could have combined 2 letters. So, when I combine 2 letters, then at the first stage of my reduction I would get 5 letters reduced alphabet. Now, once I get 5 letters reduced alphabet, then I can combine again 3 letters into a composite letter, and when I do that at the second reduction I would get 3 letters, and I have 3 symbols from the code alphabet to be allotted to this 3-letter reduced alphabet. So, no problems. Now, I could have followed another strategy. Another strategy could have been that initially I combine 3 letters. So, at the first stage of my reduction I get 4 letters. Then at this stage, instead of combining 3 letters, I would combine 2 letters, and finally I would get 3 letters. Now, there are 3 alternatives which I have suggested. So, the question is, which of this alternative should we follow? Now, recall that the symbols with the lowest probability will always have the longest code word. Furthermore, all the symbols that we combine together into a composite symbol will have code words of the same length. What this means that all letters we combine together at the very first stage will have code words that have the same length, and these code words will be the longest of all the code words. So, this being the case, if at some stage we are allowed to combine less than R symbols, then obviously the logical place to do this would be in the very first stage. So in order to achieve this, we can add some dummy source symbols with probabilities zeros and then combine all R symbols at a time at each stage of the reduction. Indirectly, by this procedure, what we are doing is that at the very first stage, the symbols we are combining are less than R, because other symbols which we added as a dummy symbols are having probability equal to 0. Why we do this is because we can, just like we proved for the binary Huffman code, that if we want the original tree to be optimal, then it is necessary that the reduced tree, we develop a code for the reduced tree also which is optimal. Now in order to do that, we have to always combine R symbols at a time. So if we wish to form an R array compact optimal code, that in any particular step in the Huffman coding algorithm, we shall combine the source symbols R at a time in order to form one symbol in the reduced source in the sequence. Now we would like the last source in the sequence to have exactly R symbols. This will allow us to construct the trivial optimal code for this source by allotting each code symbol to the source symbol. The last source will have exactly R symbols if and only if the original source has R plus alpha R minus 1 symbols, where alpha is an positive integer. So only if your original symbols satisfy this relationship where R denotes the size of the code alphabet and alpha denotes the integer, if my original size of my source alphabet is of the form this, then I can combine R symbols at a time at each reduction of the source, and this will provide me the optimal code when I move backwards. So therefore, if the original source does not have this many number of symbols, we add dummy symbols to the source until this number is reached. Now it is not very difficult to show this. Take a simple example. Suppose I start with 3 source symbols, and 3 source symbol alpha is equal to 0 and it satisfies this condition. Now if I have my 6 source symbols, so if I take, let us take an example, I have 6 source symbols to start with, and I want to do the coding using code alphabet of size R equal to 3. So if you look at this expression, we get 3 plus alpha 2, which is of the 6 is not of this form. So what it means that to make of this form, I should add some dummy variables. So if I add one dummy variable here, that is, say, make it 7, then 7 is of the form 3 plus 2 into 2. So if I add one dummy variable which has a probability of 0, then I get this relationship satisfied, and this also tells me that if I have 6 source symbols, we will try to understand the non-binary Huffman coding procedure which we have discussed today with the help of an example, and that we will do in the next class.